This is my pleasure to welcome the two next speakers. Mélanie DUCOFFE, she is a researcher in machine learning at Airbus, and Sébastien GERCHINOVITZ, he is a researcher at IRT Saint-Exupéry. He is also associate researcher at Institut de Mathématiques de Toulouse and member of the Game Theory and Artificial Intelligence Chair in ANITI. They will talk about high probability guarantees for surrogate models, and I remind that you can ask any question to the swap card chat. Thank you very much, Mélanie, Sébastien. The floor is yours.
Okay, do you hear me, Gregory?
Yeah.
Perfect. So hi, everyone. It's my pleasure to be here. My name is Mélanie DUCOFFE, and I'm here to present a joint work I did with Sébastien last year. So yes, is it working? Yes, perfect. So this work today is based on a paper we published at SafeAI Workshop 2020 with Jayant Sengupta from Airbus, which is called High Probability Guarantees for Surrogate Models. So here you could see the abstract. The paper is available online, but I would rather dig into the core subject with why we arrived at this problem. So it all happened because of some industrial needs we have at Airbus, but I guess that many industrial as well have the same issue. So the core problem is that thanks to our engineering team, we have a lot of what we call reference models that are accurate models that approximate true physical phenomenon. It could be the braking distance estimation or structure load or fuel estimation as well. And these models are really precise, so they are heavy in terms of memory, computing time, compute power, and so on. So you could not embed them on the aircraft as well. It could be great to embed them because it would increase the safety of the aircraft and help the pilots. But as it is, it's not possible. So from a machine learning point of view, what people came out is what about approximating this reference model with something that is lighter and could be embedded. So this is what we call surrogate modeling. So surrogate models are ML models, and of course, using them on board will impact the safety. And in this work, we tackled a new question about the safety of using these surrogate models inside the aircraft. So our definition of safety came with basic examples. So here I consider the braking distance estimation, but we could consider also the structure load or fuel estimation. It's quite generalized. So the idea is that surrogate models is usually a classical regression task, but the impact, the asymmetry of the error is not the same for safety. So whether your surrogate model will underestimate or overestimate your true reference model is not the same. A classical example is consider that your surrogate model for braking distance estimation predicts that there is enough space to land while there is not. It can create some overrun, and this will impact the safety. On the other side, if your surrogate model is overprotective and says that there is not enough space to land, while your reference model says that it's quite okay, then it will just impact. Maybe there will be some turnaround, and it can be waste of money, waste of fuel. But if it does not happen that much often, it's not really impactful. So this is, in this paper, the question of safety we consider. So we want to prove that a surrogate model overestimates a reference function. And the problem is, the challenge is that the reference function is a black box system. So we can only evaluate it at any point, but we have no idea of the nature of the function by itself. We cannot derive formal deterministic guarantees of overestimation, while there has been inside DEAL as well formal proof of overestimation. So it's a previous work of François Malgrir, Adrien Gaufriot, and myself, but this work is typically inducing strong assumptions on the reference model by itself. So in this context, for example, we considered that the reference model was monotonic. And here in our paper with Sébastien, Jayant, and myself, we want to generalize and have no assumption on the reference model. So what we derive is probabilistic inequalities to prove high probability safety bounds on the surrogate model, and we will see on shifted versions of it. So our definition of safety here is what we call 1 minus epsilon safe. It means that the surrogate model will overestimate the reference function at least 1 minus epsilon over time. So it's a notion of probability, and I think that the best candidate to explain you this in detail is Sébastien. So Sébastien, I'll let you the hand.
Thank you, Mélanie. So yeah, let's look in details in the definition of a 1 minus epsilon safe. So can you see my my arrow right now?
For me, yes.
Okay, thank you. So so we defined a surrogate model f hat to be 1 minus epsilon safe. So that's always with respect to a given reference function f, when the probability that f hat of x is larger than f of x, when this probability is larger than 1 minus epsilon. So typically you can think of epsilon to be super small, and you want the surrogate model to always overestimate the reference function f. So it's not always, it's to most often over approximate the reference function f. So by most often here, we mean for most configurations x in the input domain. So that would be true if we had a uniform distribution. If it's not a uniform distribution, this should be weighted according to the input distribution px. The prediction f hat of x of a surrogate model should over approximate. And in that sense, it should be safe with respect to the reference function. So like I said, there is an input distribution px. So what is the distribution of x? So we could actually choose that distribution a priori, like we could take it uniform if we don't want to give any more weights to some configurations than to any other configuration. But it could also correspond to some real data. And actually, the only thing that we assume in the paper is that we have access to samples, to independent samples, x1, xn from px. So this could be chosen. We could simulate some data and choose the distribution we want, or we can just collect some data from experiments, from real experiments, and use then these samples. So just to give more meaning and some limitations of this notion of safety, imagine for a second that the distribution px is uniform. So it means we don't want to give more weights to some configurations than to some other configurations. And imagine that we can choose the domain D on which px is supported. So let me describe the two pictures we have here on the left and on the right. So in both cases, the orange square, the square in orange is represents the operational domain. So it's the set of all configurations that we will see in practice. In red, here or here, it's we could call it the error region. So it's the set of configurations where the surrogate outputs are actually smaller than the reference outputs. So this is what we want to avoid. And the probability that f hat is, say, smaller than f of x should be smaller than epsilon, because I look at the complementary event. And this means here that the proportion of the ratio between the area in red and the area in orange should be smaller than epsilon. It turns out that if instead of considering the square in orange, I consider the square in green, the larger square, then this ratio is actually smaller. So this means that the probability is artificially smaller. So I could think that I am safe while actually I'm not safe. On the other hand, if we're in the situation depicted on the right, here by considering a larger domain of study in green, the weight of the red region is actually larger than what it is in practice. So in this particular case, the probability corresponds to a pessimistic view of the problematic event. So if you want to choose the input distribution px on a specific domain D, then the choice of D is very important. If it just corresponds to some real data, then that's very fine. Okay. So we can go to the next slide. So how do we prove that a given probability is smaller than epsilon? So here I take the probability of a complementary events. So now that's the probability that f hat of x is smaller than the reference f of x. So this is what we want to avoid. So how do we prove that this is smaller than epsilon? So just do the usual things we do in statistics. Take some ID test samples, x1, xn, and count how many times we have some problematic situations. So how many times f hat of xi is smaller than f of xi. So we just take some data and we count how many times the surrogate model is wrong in the sense that it under approximate the reference outputs. And then we just use some well-known deviation inequalities, which are probabilistic guarantees that relate how close is the unknown probability to the estimates we can compute from the data. And importantly, we don't use Hoeffding's inequality or inequalities that depend just to some 1/√n term, but are a little tighter to account for cases where the probability we want to estimate is small and we want to take that into account. So let me describe the theorem a little. So we have some random variables, x1, xn, that are some data collected independently from the distribution px. And we have some surrogate model f hat that is constructed from some training set, but importantly, the training set is independent from the random variables on which we're going to evaluate it. So how can we estimate this probability? We just compute the average number of points, xi, for which the event is true. So for which f hat of xi is smaller than f of xi. And we call this observed probability g hat of n. And then a consequence of Bernstein's inequality gives the following guarantee. So for any risk level delta, we have with probability at least 1 minus delta over the choice of a calibration set x1, xn, that the true probability that we don't know but that we want to prove that it is smaller than epsilon, this true probability is smaller than the observed probability plus some small remainder term. So maybe we can just click once, Mélanie. Thank you. So in more concrete terms, this means that for a large fraction 1 minus delta of all possible sequences x1, xn that we could observe, but we actually only observe one sequence, but among all possible sequences that we could observe, the unknown probability of error is bounded by the observed proportion of errors plus a small remainder term. So think of n as a large number, is the number of data you are in your data set. And gn hat will typically be rather small. So we are likely to have mainly this term if our initial surrogate model is pretty good. And importantly, the risk level delta quantifies how unlikely it is to observe a sequence, x1, xn, for which the guarantee fails. So this guarantee is not always true. It's true for most data that you could collect, and delta quantifies this must term. So next slide, please. Thank you. So what do we do if the bound that we have that we had on the previous slide is too loose? So we had the observed probability plus something. If the observed probability is very large, like 0.3, what do we do? Well, we could retrain the surrogate model and pray for a miracle. Maybe the new gn hat would be super small, but then we sense that we cannot do that too many times because it's cheating, repeating time and again the same experiment on the same calibration sets. We could also use a basic trick, which is to shift all surrogate prediction upwards by a positive quantity. So let's look at the picture. We have a surrogate model. And the plot here is the surrogate predictions versus the reference functions outputs. So if we want the surrogate predictions to be safe, we want them to be above the diagonal. And as soon as it's below the diagonal, it means that we under approximate the reference function outputs. So looking at the data, we could just compute the largest underestimation error and shift all predictions of the surrogate model upwards with this positive quantity. It seems to be working, but there is an issue, which is that the proposition that we showed before actually requires to have a fixed surrogate model. And we cannot play with the data as we want. So if we optimize the shift, then we are actually using the calibration set time and again. And this is the same data on which the probability of error is estimated. So we understand that here we are, in a sense, cheating. So we need to use a more rigorous way to have some guarantees for shifting. And this is what the next slide shows. So now we're going to present what is called in mathematical statistics a uniform deviation inequality. I mean, it's not really uniform. It's not uniform in that the inequality is not the same for all shifts, but at least we have an inequality for all shifts. So we have a probabilistic guarantee for all shifted surrogates simultaneously. So this is pretty much the same theorem up to some minor modifications. So here we define G of t to be the probability that the shifted surrogate model f hat of x plus t, so t is the value of a shift, is erroneous, meaning that it underestimates the outputs of the reference function. This is G of t. And just like on the previous slide, Gn hat of t is the observed probability of error of a shifted surrogate model f hat plus t. This is just the same. And what this new mathematical guarantee states is that with probability at least 1 minus delta over the choice of the calibration set, x1, xn, we have, and this is the important part, for all shifts t simultaneously, that the unknown probability of error g of t is smaller than the observed probability of error gn hat of t plus some remainder term, which is typically small. And if we want to interpret it in more concrete terms, so maybe you can click Mélanie, please. Thank you. This means that for most calibration sets, actually a proportion 1 minus delta of them, the probability of error of all shifted surrogates, so considering all possible values of t, this probability of errors, G of t, are bounded, like I said, by the observed proportion of error plus some small remainder term. And very importantly, the guarantee is valid for all shifts t simultaneously. So in particular, we can consider any shift we want, and we can consider a shift that depends on the calibration set. So here, the mathematical guarantee allows us to cheat and to choose a shift that makes us happy. Of course, the price to pay is some slightly worse constants in the bound. As you can see, the remainder term is slightly larger, but not too much larger. I would like to mention for those that know these deviation inequalities in the audience, that it is closely related to what is called the DKW inequality in probability theory, that relates the empirical cumulative distribution function to the true cumulative distribution function. But the difference here is we have a variance-like term here that enables us to get stronger guarantees than if we use the DKW inequality. And there are also some strong connections with which the literature on conformal prediction, since in all these works, they also consider some empirical quantiles on some calibrated data set. Okay, so let's see what it gives in our situation on the next slide. Thank you, Mélanie. So now we have an inequality that is true for all shifts t simultaneously, and we are allowed to choose any possible shift we want. And the inequality will be true for most calibration sets. So we just hope that the calibration set we observe is one of these most ones, but this is correct. So here we can just choose the shift T that I mentioned before. And if we choose this one, all errors are equal to 0. So we just have the last value of epsilon. And this is a proof that our shifted surrogate is 1 minus epsilon safe with epsilon to be this small number. And of course, this decreases the model's accuracy if you shift all predictions. But then Mélanie will show you briefly how we retrain the model to not deteriorate the accuracy by too much.
Can I go on? Okay, perfect. So thanks to the result of Sébastien, we have a way to have a high probability guarantee for a surrogate. The problem is that shifting will impact the accuracy of our model. So the question we ask ourselves is it possible to infer the training of our surrogate so to promote this post-processing shift and not impact the accuracy too much? So this is possible when you are using neural networks for surrogate modeling, because you can train with gradient descent and just modify the loss function. So what we imagine is using what is usually done for regression task in the literature. So you have usually the MSE, the mean squared error, taking into account the average over a mini batch of the distance between your reference function and your surrogate function. You can also have in the literature some loss function that promotes overestimation, which is called AMSE. But what we did here is to use the shift inside the mini batch, so the worst case underestimation we have on the mini batch, and use it inside the training. So if we called T this value, the worst case underestimation, our shifted MSE is just the average over the mini batch between the output of the reference model minus the shifted surrogate. And we use it with classical backpropagation to use our neural net to train our surrogate. So we applied the results we got from Sébastien on several toy datasets, but also on an industrial use case, which is a surrogate neural network for braking distance estimation. So this reference function has 7 inputs, and what we have at our disposal is roughly 500,000 training samples, and for the calibration, 200,000 samples, and the same for test samples. Thanks to this data, we were able to train a neural network with 3 different loss functions. So the classical one, MSE, the one from the literature that promotes asymmetry, AMSE, and our own loss function, SMSE, that is supposed to help get better accuracy after shifting the model. So first, what we did is train with the classical loss function in the literature, MSE and AMSE, to get a surrogate function. So the good news is that this surrogate neural network is able to approximate the reference function quite well, as we can see with the first figure. So we can see in terms of mean squared error that both of these models perform quite similarly, with 5 meters of predicted distance error. But the problem is that these models are not safe given our definition, because on the test samples, we can see that more than 50% of the samples are underestimated. So this is a true problem, but we can solve thanks to the shift option presented earlier. So we can see in blue the shifted surrogate model trained with MSE. In orange, it's the shifted one trained with AMSE. And finally, in green, it's our model trained with SMSE and then shifted. So eventually, we can see that there is a real drop in accuracy. We get from 5 meters error in prediction to roughly 100. But thanks to our shifted surrogate model, we can train with SMSE, we can see that eventually this loss function helps to reduce the drop in accuracy. And the good news is that thanks to this shifting model, we can see that it's really safe according to our distribution. So first, we can estimate the probability of underestimation on the test set. And we can see that just few samples are underestimated, and it's roughly 10 minus 5% of the test samples. But also, if we use deviation inequalities we have earlier on, we can see that the safety guarantee are 4 times 10 minus 4, which is already really low. And remember that this bounds really depends on the size of your calibration samples. So the more data you get for calibration, the better, the best these bounds will get. And now that I finished this with the experimental section, I will let the hand to Sébastien for conclusion.
Okay, so thanks, Mélanie. So just a quick wrap up of what our method looks like. So it's in 2 steps. We have a calibration step on the right. We're given a surrogate model. We can shift it upwards using a shift T that we use, that we can define as we want, like we explained earlier. So in particular, we can take the highest error. And the surrogate model on the left can be improved by taking into consideration that we will shift it afterwards. And this was our shifted version of MSE that Mélanie talked about. The theoretical guarantee that we provide is a high probability guarantee. So it's not worst case. So that's one limitation. However, it comes with a certified bound without any assumptions on the surrogate and the reference models, which is a very good thing when we're using black box models, for example, very complicated functions. As for the perspective, so we're actually working on going beyond surrogate models. So this is a work in progress. So when the label we want to predict is not necessarily a deterministic function of the input. And we're also working on some other loss functions, some other learning tests. So different type of asymmetry, different, not regression, other learning tests also. And so we believe it can be a broad setting where these ideas can be applied. So thank you very much again for listening to us, and we would be happy to answer questions.
Thank you.